review talk, so partially, and partially also contains some new results together with one of my former students, so Marian Magdi. So I guess the first part is just, I guess, to motivate why and where all these applications come from. Okay, so the overview. So there are a number of ideas that I want to communicate in these talks, right? So that you more or less know where I'm coming from and where I want to go. I want to talk about the relation between the asymptotic behavior of gravitational field at null and spatial infinity. So something that I will vaguely call the problem of spatial infinity. And then some other ideas is that, well, so there are these conditions or description of isolated systems given by Penrose, and they have been highly influential in the field. And well, so some of the realization from the community in like the last decades are that these conditions are too restrictive to describe generic spacetime, but nevertheless, they have been highly influential. And then to study this concept of study this behavior of gravitational field near null infinity and spatial infinity, so I will be using something that I learned from Helmut Friedrich when I was a postdoc more than 20 years ago, with a certain description, right, of spatial infinity, right, and this allows to pose an initial value problem for the Einstein or conformal Einstein field equation, and from there, so one can get a very detailed information about the asymptotic behavior of the gravitational field. And yeah, so the idea is that eventually we would like to use this description, right, to settle the problem of spatial infinity. I will try to explain what I mean by that. And then I want to describe application of these ideas to the computation of asymptotic charges. So this is somehow like the ideas that I will be taught here. So then there is, I want to provide this as to have everybody on the same page. I want to talk a bit about what is called asymptotias, right? And this word comes from Jon Stewart's nice book, Advanced Relativity, right? And then he has making a quote from former prime minister in the UK, right, prior to the Second World War. And he describes this as asymptotia, which is a faraway land of which we know little, right? But then this means that we shouldn't be interested, right? I think this is the takeaway from this quote from Jon Stewart, right? So we know little, well, maybe at the time of this book was published, we knew little. I think we know now quite a lot. And well, just I guess in quickly, so that there is a vast literature on the asymptotic gravitational field, and most of these, or at least a big proportion of these, really builds on Penrose characterization of the systems in general relativity using and the notion of asymptotic simplicity, right? It's due to Penrose, and then in all this vast literature, which was I think largely built in the 70s and then 80s. Much of it is formal, right? Let's say that it makes a number of assumptions about the behavior of the spacetimes in the asymptotic region, which may or may not be generic, right? And well, I mean, these assumptions, right? So as always, as people say, so the devil is in the detail, right? So we really need to understand these assumptions, right? And the genericity of Penrose ideas, and then, well, people have spent decades working on this. And well, certainly, I think in top of my list, right? Because this is somehow the formalism that I learned Helmut Friedrich. Invested a huge amount of research time thinking about this. And then I learned some of the techniques also from him. But then other people, right, in the mathematical relativity community, like Peter Crucier, Robert Bye, Bernd Schmidt, have also looked at this. And then, of course, coming from the side of, say, stability of the Minkowski spacetime, there's the work by Christodoulou, Kleinerman, and then Kleinerman, Niccolo, Lindblad, Wapniansky, so on. So people using all these vector field methods, trying also to understand these assumptions, right, and the behavior of the asymptotics or gravitational field. And more recently, using different type of toolkit. So Peter Hinz and Andras Vasi also trying to understand how the asymptotics, right? In general, and I also should mention Leonard Kerberger as well, that's also made contribution to this. And although I think it's fair to say, right, that there is a great progress in the subject, right? I think what is happening is fairly well understood. I think that there are certain things that need to be settled down. Yeah, so some work is still required. Of course, so this list is somehow slightly subjective, right? Or based on somehow my particular interest, and obviously it's not intended to be comprehensive, but I think anyway, that should give you some good idea. And well, yeah, some historical context, right? So I think I want to make use of, I guess, like a starting point. I want to well mention this definition of asymptotic simplicity by Roy and Penrose, so dating from the early 60s, right? So I think I'm sure most of you have heard this definition in one way or the other, right? Basically, you say that asymptotically simple space-time, you call that asymptotically simple if it's possible to construct some sort of a conformal extension of space-time with certain properties, which it looks like the asymptotic, to some extent, like the asymptotic conformal compactification of the Minkowski space-time. And the requirement of Penrose was, so the classic definition is the smoothness, right? So you require this extension is smooth. And then if you look, say, in Penrose and Rindler, for example, then so there are versions where there is a certain, they don't make it smooth, but you only have a certain number of the derivative, right? But then you get the gift, right? And then if you have space-time with certain properties, so then there are a number of consequences that follow from this, right? And it can be a formalism, right? And so basically the idea is, well, so the motto behind this is just to provide a geometric framework to study the asymptotic relational field. So you regard this as somehow trying to capture certain universal properties, well, for behavior, and then you try to extract consequences from that. And well, as just I guess as some sort of advertisement was what we did somehow backdated, right? So last year we have a meeting in the Royal Society here in London, and you just mentioned this was because this turns out that was pointed out by Paul Todd at the time that probably was somehow celebrating the 60th birthday, right, of the idea of spatial infinity, although somehow the timing was not really intended to be this, but it was somehow sort of a serendipity. All right. So there is this point in this definition by Penrose, right, of asymptotic implicitly, that so the key idea there is that the smoothness somehow encodes some sort of the information about the decay of the field, right? And then, in fact, if you have smoothness, you have a very particular type of decay with it's called literature peeling, and I will say something more about that. And then there is also a sort of corollary of sorts, right? That if we're in situations where there is restricted smoothness, then you also would expect some sort of modified decay, right? So basically, that the smoothness would affect the peeling, right? So you only get peeling if you have a certain threshold of regularity. Okay? So peeling. So what do we do mean by this, right? So just to be also on the same page, right? So peeling is a certain theoretical decay of the various components of the Weyl tensor with respect to a certain frame, which is somehow adapted to the radiation process. So in the asymptotic regions, I will say a bit more about this later on. And then also you see that you have the slowest falling component, falling like 1/r, where r is certain parameter along generators of outgoing light cones. And then also there is, let's say this hierarchical behavior, right? Until you go to psi 0, which is the one that falls off the fastest, right? And then the psi 4 is somehow the radiation field, right? So this version of the peeling is in some way due to Penrose, but then so just to mention that, in fact, this observation of this spinning behavior is actually really due to Bondi and collaborators, right? But not somehow in this Penrose, Newman-Penrose notation. Okay, so so you have this idea by Penrose, and then you want to understand how well, whether it's useful to describe physical processes or physical systems, right? And then for this, also you have to, there are some questions that you like to assess. One is how large is the class of spacetimes that need this Penrose compactification? It's a natural question, right? To say whether if you can somehow think about the space of solutions to the Einstein-Feld equations, or the moduli space of solutions is something like open set, or you have isolated islands, or yeah, so it's something that you like to understand. And the second one is well, so how will you construct this space-time in a systematic manner? And one way of doing this is through an initial value problem, so a Cauchy problem. And somehow it seems plausible, at least, that extra conditions are required, right, to achieve this, so to obtain space-time which are smooth. So I think it's like a spoiler alert, if you want, right? So there, so you would expect that space-time with a smooth Penrose compactification are not generic. Okay, right. So without going too much into the details, right? But so there is one substantial problem arising here, which was identified originally by Penrose, right? And then Helmut Friedrich, I think put it in a more, clear manner many years after, which is, so the observation is the following, is that when you do the conformal extension of the Minkowski spacetime, or the classic conformal extension, so you get a setting where everything is super smooth and regular. However, as soon as you have a spacetime that contains non-vanishing mass, right? So then there is a singularity at spatial infinity, right? So this is, and this is a source of troubles, right? Yes, and this somehow makes, so what I think you want the essential difficulty, right, to deal with in the analysis of spatial infinity, right? So right, so one way of thinking of this is I have this picture here, right, where you have somehow like a Minkowski-like space-time, right, with spatial infinity, as you have some initial data, and then your space-time, your data has non-vanishing mass. So then somehow the picture to have in mind is that there is some sort of singularity, somehow like the naked singularity of negative mass Schwarzschild, but emanating from spatial infinity, right? And well, I mean, if you want to have a more like three-dimensional picture, right? So then you can look at this cone, right? That this cone again is scribe, and then the space-time, which is this region here, is the region outside the cone, right? So right, so I guess aware of this, of the difficulty, I presume, right? So so Helmut Friedrich tries to understand whether you could construct spacetimes with a smooth conformal extension, right? So which are asymptotically simple, right? And then as a first problem, right, or partial problem, he considered the evolution from hyperboloidal data, right? And then so the point from this hyperboloidal, so the point about this hyperboloidal data is that these initial hypersurfaces avoid spatial infinity. So these complications, right, that arise from this conformal singularity, so singularity from the conformal structure from spatial infinity are avoided. And then by using some methods, which I'm not going to say too much at this moment, so he was able to show that you take some hyperboloid in Minkowski, you consider now the preparation of this Minkowski data, hyperboloidal Minkowski data, you can show that you can recover to the future of this hyperboloid, so you can recover somehow the full future of the data, right? And then what you obtain is a part of space-time, right, which has somehow the same asymptotic structure of Minkowski, with a point that as representing time like infinity, where all the null generators of null infinity intersect. And well, I think it was already in the paper by Helmut Frick, so he already now discusses the question of whether you can push this hyperboloid back down to spatial infinity. What do we require, right? To actually, instead of having the hyperboloidal problem, you will have really a problem with a proper Cauchy data, right? And well, the reason for this question is that, of course, from hyperboloidal data, so this is semi-global, to say that you cannot recover the full space-time, but only so whatever is to the future, right? Or in the past domain of dependent, right? So it will be, which is now limited by this dashed line. Okay, I guess that another ingredient or a contribution to this study of asymptotics, right, is the nonlinear stability of the Minkowski spacetime by Christodoulou and Kleinerman, where they do start with some Cauchy hypersurface, and then they consider a certain class of initial data, and then for that Cauchy data, well, so they recover the global spacetime to the future, right? Yeah, and but and then they can see that this spacetime has a full scribe. But then what they observe is that they are not able to the estimates to recover peeling, right? So to say that a priori it seems that the spacetime that they are constructing, they have they don't satisfy peeling, and then the scribe is non-smooth. And I think that at the time, right, so this, as you see, in 1990s, it was not clear whether this is really it was some sort of technical aspect of the analysis, that the estimates were not sharp enough or not. But well, now I think it's clear, right, that it was a question of a fundamental question, right? A fundamental reason that they were not able to recover this full scribe. So this smooth scribe. Anyway, somehow a way or a trick, right, to get around this somehow this use of the hyperboloid, right, is came about with the gluing techniques, right? So this is building from this was done by Pierre Cruciel and Erwan Delay. So this is really building on the work of Corvino and Schoen. And then the idea there is that so these gluing constructions allow, given some initial data for the Einstein field equations, it is possible to glue a compact region of this data with an asymptotic region, which is, say, for example, the Schwarzschild spacetime, right? So that you start with something which is somehow arbitrary, then there's a transition region, and then in the asymptotic region you get the Schwarzschild, and you can do this with data which is also somehow in this blue region a perturbation of the Minkowski spacetime, right? And then in this way, right, through this gluing technique, so what one is able to do is to construct, right, an hyperboloid, which is this line in blue, which actually enters into this red region, which by construction has to be that of the Schwarzschild spacetime, right? And then, so basically through this gluing construction, so you are able to evolve from the Cauchy hypersurface to the hyperboloid, right? Like you want almost trivial way, and then from there, right, if you can control the size of the data on the hyperboloid, then you can complete make use of Helmut's semi-global stability result, try to recover the full of the complete scribe. And then I think the question whether it is, well, so there is something artificial in this example, right? So the question is whether this is the only way of you can do these things or not. And then Helmut Friedrich, then I started a program of research to try to understand these things, right? And in fact, this program is actually prior, right, to the results of Krushel and the delay, right? And then, so in particular, what we wanted to do is to obtain, well, you analyze spatial infinity from the point of view of an initial value problem, right? And then, the key for this is try to obtain something where the equations are regular, and also the data is also regular, right? So that you are able to control somehow the solutions coming out, arising from the solutions to this initial value problem. And then he called it the regular asymptotic initial value problem as spatial infinity. Right? Again, this is very high level, right? So I'm really like skimming over the details. Right. And I think a central aspect of this, which I'm going to use in the later parts of this talk, is something that is called the cylinder at spatial infinity. But then this idea can be also seen in the literature in a slightly different way and presentation in the work by Ashtekar and Hansen and by Baig and Schmidt. So although I think the motivations of all three somehow perspective on this are slightly different, right? So the key idea is you start with standard somehow representation of spatial infinity as a point, right? And then somehow this spatial infinity, point of spatial infinity somehow is a point where this past null infinity and future null infinity meet, and then we also have some Cauchy-Eppert surface meeting here, and then by certain construction, you blow up this point into something which is a cylinder, right? With, say, in the simplest way, sections which are two spheres, and then the cylinder has the property that allows to transport information between past null infinity into future null infinity, and well, part of the ingredient is that it uses certain geometric preferred objects, or conformally preferred objects, so called conformal geodesics, and then all this construction is based on the properties of this curve. But I think this point is not so essential, although, well, I mean, it plays a role in writing the equation, but it's not truly essential. Well, and I guess a point that to make in this picture is that this is a picture which is highly distorted, and it's also not a conformal diagram. So if you want, it's some sort of a diagram in a particular set of coordinates. So that's why in this representation, so you can fix things in such a way that spatial, so null infinity looks like a horizontal surface, right? And say same thing for past null infinity, right? And whereas in the case of the Penrose diagram, so then we stick really to the convention that lines at 45 degrees describe null hypersurfaces, right? And then an essential point about this picture is that well, so there are these sets which I'm putting here in lila, so called I minus and I plus critical sets, which somehow are the intersection, right? The points, or the sets of points where past spatial infinity meets null infinity. And then I guess for some of you that know about this, so there is this picture of hyperboloid at spatial infinity by Ashtekar and Hansen. It has been very influential in the literature, and well, so having discussed, right, for like decades probably, right, that the Friedrich representation and Ashtekar and Hansen somehow should be related to each other in some way. And somehow some years ago, so we actually work out this relation my student Mariam, is the one who did most of the calculations, right? And then you can show that there are a certain number of assumptions, right? So you can bring these two representations together. Okay. So now, so this cylinder spatial infinity has a number of remarkable properties. And again, I'm skimming over about this, but this is somehow an idea that I will come back later. So this property, the key property is that the cylinder is a total characteristic of the conformal Einstein-Field equation, right? So the equation that we'll use to describe this conformative rescaled space-time, so following somehow Penrose's point of view. And so this means that the evolution equations reduce to a set of transport equations on the cylinder, to say that if you have information, right, about your data at the intersection of the Cauchy-Hyper surface with the cylinder, so that you can actually integrate the evolution equations without needing to further information outside. And this allows to basically to evolve just part of your solution, right, directly on the cylinder, right? So in this sense, although this boundary is not like a normal boundary that you would say in the case of the say anti-de Sitter space-time, right, or another boundary value problem, right? So it's even more special, right? So it doesn't allow you to put any boundary condition, right? So to speak, the behavior of the field at the boundary are already detected by the data, right? And there's also from data on the initial hypersurface, so at the intersection of the initial hypersurface, you can construct then see what the behavior of the field are at these critical points. And then you can also do this with higher order derivatives somehow in the radial direction. And then so this allows you to construct what is known as the solution jets, right? So then the components of the solution jets, you can think of them as being like the coefficients on a Taylor-like expansion with respect to some radial coordinate, right? So then, so basically the idea is that using this property of total characteristics, so you can construct a type of asymptotic expansion that allows you to relate about properties of your data with properties of the solutions at null infinity, so both future and past. Right, and right. So from looking at these jets, right, to the solution, right. So then one can conclude somehow with certain amount of work that null infinity will be generated. It will be non-smooth, right? So the regularity of this coefficient on these jets, and then say think in particular, I think about say the value of the components of the Weyl tensor in some particular respect to some particular frame can be computed explicitly. Well, and then somehow the only limit are computational complexities. You need computer algebra really to explore this in some detail, right? And at some point, somehow the computer doesn't want to work more. But then what you see is that this solution, right, that you approach these critical sets, they develop certain logarithmic divergences, at least for a certain type of data, right? So there is an assumption about data here, right, that I somehow have obviated, but okay, so you somehow assume that you have consider data which is as smooth as you want, right? So they, for example, that can be expanded in powers of 1 over radial distance, okay, right? So you and then you see that even this very nice data will numerically develop logarithmic singularities. And then so the nice thing about this framework is that actually allows you to see from which pieces of the data these logarithmic singularities arise from. So and then so you can play the game of somehow fine tuning the data so that certain logarithms disappear and so on, right? So you can this formalism allows you to do a very nice fine tuning, right? If what you want is to eliminate logarithms, right? And to give you an idea, right? So one can do some calculations, which are formal in a sense that I'm going to explain. And I did this some years ago with Edgar Gasparin, which I think is here in the audience. And then, so what you have is you consider time symmetric data for the Einstein field equation, and then you also consider data which is has a nice behavior at spatial infinity. So in particular, it allows a point compactification at spatial infinity. So so the definition of this, what it means by this, is given in this statement here, right? But basically, it means that you have some physical data that can be compactified. You can add a point at infinity, and then you do this by having a conformal factor such that this conformal factor vanishes at this extra point you are adding. Also, it's gradient, but then the Hessian is not degenerate, right, and has certain normalization. And then, in fact, you can set up coordinates in a part, so the coordinates on your initial hypersurface in such a way that the tree metric is actually flat to a very high order, right? So usually you have normal coordinates, and then corrections to the metric come to order, so say norm of x squared, but then you can also use conformal freedom to actually gain a lot of an extra power, so to speak, on the decay, right? And then if there is a space-time arising from this data, right, and then this is somehow the big assumption, right, and then you can compute what would be somehow the peeling behavior of this space-time, right? So, and then you see that for this data, and then so you obtain generically this so somehow, so you cannot recover peeling, right, for this class of data. Right? So you see that the components, say psi2, psi1, and psi0, right, so they fall like 1 over r cube, and then there is a logarithmic term appearing here. Right? So this is basically, if you take this data satisfying the function 1, I think there's a typo here. Right, so this on so this on tamper, right, and then, right, but then, so you can do fine tuning, and then it turns out that at least part of this fine tuning can be done through specifying the behavior of the Cotton tensor. So you have to compute the Cotton tensor, which is conformally invariant object, right, related to the metric. So which characterizes, so it identifies conformal flatness, right, for your data, right? So in particular, if the Cotton tensor vanishes in a region, right? So then you know in 3 dimensions, or also in higher dimensions, you know that the manifold is conformally flat, right? So it turns out that there is a condition, right? So that if you want this Cotton tensor actually to vanish, you're only at the point at infinity, right? So this condition really at one point on your conformal extension, then you gain certain orders of the decay, right? And then if you start requiring a bit more, so you require not only that the Cotton tensor vanishes at infinity, but also the derivatives, then you gain even a further yeah, so you are almost there, almost in the case of peeling, and then by looking at putting conditions on the second derivative of Cotton, then in fact you recover classical peeling, right? So this again, so is there is a key assumption, right, which is somehow that you are assuming that actually you have a space-time, right, arising from this data, and in fact, so to speak, you actually can cover this assumption, right, through the analysis by Lydia Vieri on the, so she has wrote a more general so obtain a more general proof of the stability of the Minkowski space-time by Crittenden and Kleinerman, right? And then the data that I'm using here actually falls into Lydia Vieri's framework. But anyway, so this is just, I guess, the point that I want to make here, right, is that actually there is in principle a mechanism, right, on how to relate conditions of the data and asymptotic behavior, right, and verify whether you have peeling or not, and if not, what sort of modification you would expect. Of course, this is very dependent on the specifics of the data, and that's why we were using here something that is time symmetric and with very nice point compactification, right, just to avoid technical complexities, right, and then be able to do the calculation. Right, and just very quickly, right, although because it's the one can actually check, right, that in this particular framework, so space-time, you would expect to have nice properties at spatial infinity and null infinity, like time-independent solutions actually do have this property, right? So in general, so you can, in particular, so right, so that there is this theorem, right? So you can show that static solutions actually are as regular as one would expect for near spatial infinity. This was done originally by Helmut Friedrich, and then together with Andres Acenya, we generalized this to the stationary case. And then this sort of, we hint that at least for certain classes of data and certain settings, it may be plausible, right, that there is a sort of rigidity implied by the smoothness of spatial infinity. Right? If you want solutions to be smooth as spatial infinity, then you are actually restricting in a very heavy way the class of spacetime that you can bring into play. And I want to say much more about that. But I just want to mention something that is what I find particularly, especially interesting, and I think it's a great development in recent years. And this is the work by Hinz and Bashi. And then so they using methods from what's called the geometric scattering school, right, of Melrose. They obtain a new proof of the nonlinear stability of the Minkowski spacetime, and the nice thing about this proof is it allows to assert that you can obtain spacetimes which have polyhomogeneous expansion, right? So to say expansion of spacetimes with asymptotic behavior like the one I was showing before, right? So with the expansions are in powers of 1 over r and logarithms, right? And then these spacetimes are rigorously constructed, and then you can compute these things to expansions explicitly. However, so I guess a critique, right? So from my point of view, the way I understand the work is that the result is not completely sharp, right? In the sense that they so I think one could actually refine the asymptotic expansion, right, and eliminate some of the logarithmic singularities that they have. So some of these logarithmic singularities or logarithmic terms may be gauged there, right? So so they don't do this analysis there. I think they were not really interested. It was not really the focus of their analysis, but more actually the construction of polynomial expansions, right? But I think the question is still open of how you can sharply, right, establish this correspondence within data and the actual form of asymptotic expansion. Okay, so I think this is there for the future. And well, I've been talking about spatial infinity for a long while, right? So I guess you could ask, so why should one care? Well, I think yes, I think on the second part of this talk, which I will come shortly, I think so that there are somehow physical motivation really to go and mathematical motivations to do into this. And then I guess that the other point that I want to make, and sometimes is not appreciated, is that although a lot of this analysis actually come from the stability of the Minkowski spacetime, right? Because somehow it's like a natural case to do, right? So you can you can actually localize these discussions near spatial infinity, and then you can actually consider more general classes of space-time, right? So space-time with a black hole or so, right? So many of these discussions are actually independent from the setup of stability. And then as we make use later on, so Friedrich's cylinder spatial infinity also provides a framework to study asymptotic behavior of a certain quantity defined at null infinity, in particular asymptotic charges, and how these are related to initial data. Okay, so this is somehow, I guess, a very long introduction, and then I want to talk about a particular application, right, which I did with Marian McVie. Just very quickly, for just to also set the setting. So what we are interested in discussing are known as DMS charges, so Boson-Mesner-Sachs charges. And this comes from the observation, right, that the symmetry group of null infinity is this DMS group. And so this group is made of asymptotic symmetries, which are solutions to the asymptotic killing equation. That's to say, you try to solve the killing equation to a certain order, right? And the idea is that these asymptotic symmetries are transformation of Scri that in some sense preserve the structure. And why we care? So there are a number of conjectures coming from the community of high energy physics that somehow where these charges are involved. So one of them is what you mentioned, the symmetry, but then there is this conjecture or idea is presented in this triangle, which I don't fully understand very much, but I thought I had to mention this. It's also tied with a gravitational memory, and also through this soft graviton theorem in higher energy physics, right? And then in a way, so probably most of you know, I had spent a lot of time working with spatial infinity, and then at some point I decided to make like a break on this, but then somehow I guess I made a break on this, but then I came back because some people in this high energy physics were actually making some statements regarding which involves spatial infinity, which didn't seem to me correct, right? So then I was motivated to check what didn't sound to me correct from the time I was working on them. So I decided to have a look again, and then I somehow I brought along Marian into this. Okay, so what I'm going to say in the next will be mostly concentrated with super translations, right, which are reparametrization of the null generators of null infinity, right? So basically the idea is that you have some code on Scri, and then you come up this code to another code on Scri by adding a certain to the parameter, right, of Scri. So I'm calling you are adding certain function, right, of the spheres, right? So this translation is associated to So this is the way somehow you define this super translation. Okay. And I guess so one of the things that always makes this discussion of questions of null infinity is that most of the discussion is always set in a particular set of coordinates, and then there is a frame, right, that is recurrent in the literature, which is called the Newman-Penrose gauge, right? It's a certain type of coordinates, choice of coordinates frame, and conformal scaling, which is adapted to the geometry of non-infinity. And well, I don't want to give too many details on this, so I will flash a bit on this, but then this involves setting some coordinates, a frame, and then there is a very precise way of setting things up, and then you can actually also make use of conformal freedom that you have the setting to fix some components of the connection and the Ricci tensor as well. Okay, right. So so when you are looking at these BMS charges, right? So then first thing it's trying to get intuition is to look to the linearized equations, right? And then we start by looking at the spin-2 equations, right? So we look at solutions to this equation, so the spin-2 equation, right, in Minkowski. And then, so it turns out that these BMS charges associated to these spin-2 equations are given by this formula. So you take the Coulomb field, the component field corresponds to the Coulomb field of your spin-2 field, right? And then you take a certain smooth function on the sphere, right? Which basically is the one function defining your super translations, and then you can decompose this function with in terms of spherical harmonics, right? And then in particular, you can make your life simple and just choose a particular y to integrate against, right? And then so this will give you the so-called BMS charge. And and then you can construct these charges. You can take a certain cotton scry and another one, and you can construct these charges at different cuts. And in general, you will see that these cuts, the value of the charges are different at two cuts, right? So, and in fact, you can also write a balance law for that relates somehow, like there's a sort of flux of the charge, right? So that you can quantify the difference between these two charges, and so you can do the same also with scry minus. But then one particular question, right, is whether, so what is the limiting behavior of the charges, right? So if you take some cut in scry, and as I said, the value changes from cut to cut, but then, so what happens when you go towards spatial infinity? So you put these cuts towards I0, right? So whether these charges will be that well defined when you take the limit first, and if so, what happens with the other set of charges that are naturally defined or are past non-infinity, right? Whether do they agree? And people have looked at this in different ways, right? And well, I just mentioned it here. So people that work on this, like Andris Strominger and Henault and students, and then Kartik Prabhu. Yeah, so each one has looked at this with putting certain ingredients and making certain assumptions. So somehow our idea here in this project was really to make use of Helmut Friedrich's cylinder spatial infinity. And the idea here, and I think the big advantage or telling point, is that we have to make certain assumptions to make things run, but these are actually controlled in terms of initial data, right? Rather than at some points on your space-time, so how in the development of your space-time, so that anything that you are assuming actually can be charged to the free data, so to speak, right? So we are not running out of funds here. Okay, so this is somehow the motivation behind, right? The rationale. And then, as I said, also this again really makes up of the cylinder spatial infinity, which I mentioned before. Right? I don't want to say too much again from this, right? But this now the generic framework I described before, but applied to the Minkowski spacetime. And well, so the I guess the key difficulty, right, in this analysis is that you have to translate between the gauge in which this setup of by Helmut Friedrich is what the gauge that is used in that setting, and say the way in the Newman-Penrose somehow gauge, right? And then you can do certain, so you can work this out explicitly in the case of Minkowski, right? So and then you can obtain somehow the Lorentz transformation that does the trick explicitly, right? And somehow the key ideas from this really borrow really from Friedrich and Canard, which they did this for a generic spacetime, and right, but then well, asymptotically, so to speak, right? And then you can work out things say globally in the interior of the spacetime. And right, then so to compute the charges, right? So you have to look into the Coulomb component, right, of the spin to field, right? And then for this, there is another assumption, right? So you have to make like a guess of how your solution will look like. And then we are looking for solutions to that to leading order, right? They admit an infinite number of harmonics, right? And then so to think that this solution in this conformal scale picture, right? This doesn't go to zero, so then it's a complicated function on the sphere, and then with a coefficient that depend on time, and then some all lower order corrections. So this in the literature on the topic, so people will call this boosted, right? In the sense that you are allowing for a certain number of harmonic modes, right? And usually, so most people work with things that go to linear order, like so only have the y00, so the one a linear order. And in fact, because the equations are linear, actually you can actually check that there are solutions to the spin to equations with these properties, at least near spatial infinity. And well, so just so basically what you have to end up doing is computing the coefficients on this expansion explicitly. And these coefficients are functions of time, and they solve the Legendre equation. And then so you can write everything explicitly, and then so the solution to the Legendre equation, they have two parts, right? So you have a solution which is the Legendre polynomials, which is completely regular, and then there's another bit which is singular, right? Which is called Legendre functions of the second kind, where the singular behavior is clearly well understood and is basically to the order a log, right? So then you have explicitly all the information that you need to compute the charges. And then from this analysis, it becomes clear, right, that you can really actually fine-tune the data, right, so that the charges are well defined, and all, yeah, so basically, right, and then so you get some funny parity conditions, right? With the case of these are not really super important, right? So I think it's just important just to know that you get these parity conditions which determine the conditions so that the charges are well defined, and more importantly, so that this condition actually can be specified in terms of free data, right? So there are several ways of doing this. And one of them is using a trick or some observation by Anderson, Bagdal, and Judio, where the solutions to the spin to equation, to the constraints to the spin to equation, which is you can call this the Gauss constraint. So it can be written in terms of you give some arbitrary spinor, which is the free date, and then there is an operator, right, that somehow that singles out the part that satisfies this equation. Okay, so then you can actually check that things can be expressed in terms of free data. Okay, and then I guess the other part, so somehow from a corollary of this is that the charges are generically not well defined. But then when they are defined, and in fact, yeah, so the data will, so the charges will only be defined if you fine-tune the data, right? As I was pointing out. But moreover, also, if in the case where the charges are well defined, then you actually can then verify, right, that are correspondent with the charges. And then so in the literature, right, say the work of Strominger, so this is actually so this identification is somehow put by hand or as it's a consequence of something that's called the antipodal matching. So they put by hand a way of identifying future null infinity and past null infinity. And well, somehow here the identification arises naturally, right? In fact, you can think that this antipodal matching is somehow, if you want, a regularity condition, right? And I think this was, not really properly appreciated from the analysis of the original calculation by Strominger. Okay. And as I'm taking too much time, so I just wanted to briefly talk about I think the most interesting case, which is BMS charges in general relativity. I will go a bit faster, right? So the idea is somehow the motivation and the ideas behind are somehow similar as the linearized case, right? Of course, more convoluted and complex, right? Because you are working with the conformal equations, right? The full equations. And just to mention that this again work with Mariam and then with Kartik Prabhu. It's about to appear. And right, so just I guess I just will stress the points of difference here. So the expression for the charges of the BMS charges in the case of GR is a bit more complicated. So in addition to the Coulomb term, so you have a correction term that involves you want like a radiated part of the gravitational field, which involves this shear tensor, okay, and derivatives thereof. And again, so you, as always, right? So a key point, right, in this analysis is to try consider a proper class or a class of initial data, right, for which the charges are well defined, right? And it turns out, right, by looking at, so I'm doing some say, back of the envelope calculation, turns out that things that are, so you need to involve data which is boosted, right? So otherwise somehow the charges are not, so will be trivial, right? So you want to consider class of data for which, yeah, so the charges have interesting values. And as it turns out, so there is this paper by Lan Huang, so 14 years ago, where again using gluing constructions, right? So so basically they construct data which somehow prescribe asymptotic behavior at infinity, and from those we consider data of this form. So this, so I particularly pay attention. I want to make focus on the tree metric, right, which contains the usual like Schwarzschild-like mass term, but then you also have other terms that go like 1/r, right? And then these they involve a function of the angular coordinates, alpha, which somehow is the part that contains somehow the boost information, right? So this can have all sort of harmonics in expansion. And then also for the fundamental, the string curvature, so then you also have some function beta and some constant vectors, right? So somehow we were very lucky, right? So this already was somehow given for us in the literature, and again, so the idea is that you make use of the fact that spatial infinity of the cylinder is a total characteristic, and then this allows you to compute now expansions now not of the spin to field, right, but of the full solution to the conformal field equations, right, near the cylinder, and in particular for components of the Weyl tensor and the parts somehow of the solution that involve this shear tensor. Well, and then of course as well the transformation, so the Lorentz transformation and scaling that connects the Friedrich gauge and the Newman-Penrose gauge. And again, so you can imagine, right? So the idea is similar, as I said, right? So this actually, so the previous calculation could be done, or spin to field could be done by hand. So this here you really need to use Mathematica for this, and then you have a behavior for the spin to field, right? With that again admits a number of harmonics in principle, and then again, so you can write solutions to this, right? Solutions to this Legendre equation, right? With the line, the polynomials giving you the regular solution and the Q giving you the singular part. And somehow something that is remarkable from the analysis, and we won't have to go very deep into the expansions to assert this, is that the shear tensor actually vanishes at a partial infinity. So to say that, in fact, the charges, although you have this extra term in the charges, when you take the limit to these critical sets, in fact, somehow the value is actually formally the same, right? The expression is formally the same as for the spin to field. And well, again, as you may not be surprised by now, so these charges are generically not well defined. And regular solutions are actually, but somehow this is actually a difference between the spin to field and GR, right? So actually, because the constraints are different, right? The GR constraints are actually stronger than the ones for linear gravity. So actually, the regularity conditions are more stringent, right? So to obtain regular solution, you actually have to kill the harmonics with the data which have odd parity. So it's to say that in this full GR case, at least for the class of data that we're making use of, you actually have only half of the charges than in the linear the spin to field case, right? So this was actually a surprise. And then, well, so these charges again, well, they are really, when defined, they actually give in terms of multi-Floer structure of this function alpha, and then you can identify, establish the identification between future charges and past charges. And again, I stress this, right? So the key point is that you are not making use of this modal map, right? So everything, this identification comes actually naturally once you are restrict yourself to the class of data where the charges are well defined, right? So you have to fine tune so that the charges are well defined, and then if it's the case, then you actually can identify them, right? The ones of the future and those to the past. And yeah, I guess this is somehow the main idea that I want to show to you. And just to wrap up, so I guess some conclusions and takeaway messages. So I think, yeah, the message I want to convey is that there's this representation of partial infinity due to Helmut Friedrich, which can be used, right, to understand some of the assumptions, right, or the assumptions behind the asymptotia, right? So this study of non-infinity. And then you start using this very quickly, you realize that some of the assumptions, standard assumptions, are not generic. So, and I guess this is a cautionary work. And so I guess so of course, a lot of people like to work with a space-time perspective, right? But I think the advantage of this approach is that what you are doing is you're making assumptions on free Cauchy data, right? So then you know that you actually, in principle, the thing that you are, the data that you are making use of should all to be able to construct them, right? From a Cauchy initial value problem, right? So what lies ahead, right? So, well, of course, so there is a point here is that these expansions, right, despite being so useful, they are still at the level of format. So there's always this underlying assumption here that actually there is a space-time, right, having these asymptotic expansions, right? And this somehow is a point that requires more work, in my opinion. And the question is how you do this, right? So it may be that the methods of Hinz and Bashee give you a way of doing this, for example, or you have to do something else. The future will tell. And yes, I guess with this, I will I should stop. So thank you very much for your attention.